Welcome to this Rilem webinar entitled From Non-Conventional to Non-Negotiable, Bamboo as a Mainstream Construction Material. The intent of this webinar is to give a relatively broad view of the present state of practice for the use of bamboo as a construction material and to describe some of the efforts and approaches being used to move bamboo into the construction mainstream, truly shifting bamboo from being a non-conventional material to one that's regularly specified and used, making it non-negotiable. So first, a little bit of motivation. Why bamboo? Well, we're all familiar with the litany of statistics associating the building sector with, let's say, global CO2 emissions, massive extraction of natural resources, and so forth. Couple this with demand. Required building floor area is said to probably double over the next 30 years. So regardless of improvements in efficiency and our ability to change these trends, the construction sector clearly has a dominant role to play in both mitigating the global climate disaster and acclimatizing society to the new normal resulting from climate change. Shifting the reliance of the construction sector away from resource and energy intensive materials such as concrete and steel and toward bioresource-based materials is one component. It's one tool in our toolbox required for reducing the overall impact of the construction sector. So focusing on bamboo in the built environment, I'm going to place bamboo on a spectra. And so we can talk about full-culm round pole bamboo construction. We can talk about marginally engineered bamboo, where the product still certainly resembles that full-culm form, but has some degree of fabrication associated with it. And then finally, engineered bamboo composites. We think about glue laminated bamboo, Scrivener, and so forth, that usually take a form factor closer to what we typically see in timber construction, for instance. And if we place these into the built environment, we have standards, we have specifications, we have codes associated with these. And so in terms of the raw material itself, we have test methods specified by ISO 22157. And of course, these are appropriate across the entire spectra. We have grading standards associated with bamboo culms, bamboo poles, ISO 19624, and these are certainly appropriate, possibly across the entire spectra, but certainly for full-culm and marginally engineered bamboo. And then we have design standards. For full-culm marginally engineered bamboo, ISO 22156 is appropriate, and for engineered bamboo composite materials, I'm going to make the argument that we can generally use, existing design standards for engineered timber, Eurocode 5, the NDS in the United States, and so forth. So first, a bit of a history of bamboo standards for building structures, and these all reside currently as international standards promulgated by ISO. So, going back about late 1980s, it was proposed that a suite of materials and design standards for full-culm bamboo for round pole bamboo be developed. It took about a decade to get this off the ground, to get enough material behind it. And that resulted in the promulgation in 2004 of the two initial standards, 22156 for structural design and 22157 looking at determination of physical mechanical properties. Now, both of these 2004 standards are what I refer to as version 0 documents. They're intent signifying, but in many cases they don't really have enough. They're not sufficiently robust to actually, let's say, design a structure with. They tell you what we want to accomplish, but don't necessarily tell us how to get there. Skip forward another decade, and we began looking at initiation of a revision procedure for these documents. This resulted in 3 documents in relatively quick succession. First, a new document, 19624, that looked at bamboo structures and particularly the grading of culms, something that's going to be important and is actually necessary for the design of structures. In 2019, a significantly revised version of 22157, determination of physical and mechanical properties of bamboo culms, so improved test methods. And in 2021, a significantly revised standard for structural design, 22156. And we'll talk about each of those. Since then, the ISO committee associated with this has moved into looking at engineered bamboo products, promulgating 2 sets of test methods, one for full member properties and one for using determining member properties using small size specimens, so-called small clear specimens in language used in timber. So that's 22478 and 5257, excuse me, and most recently a product specification for glue laminated bamboo, 7567. And the ISO committee is continuing to promulgate standards for engineered bamboo, including potentially a design standard for engineered bamboo, and revising and maintaining the existing full-culm standards. April 2024, Rilem initiated first technical committee on bamboo and material characterization of bamboo, and really one of the clear motivations of developing this committee is to support the efforts of standardization at ISO. ISO doesn't have terribly active technical committees. They focus on writing the codes, and so the Rilem Technical Committee can actually work on developing test methods and standards and specifications that can then be promulgated by ISO. So let's take a look at the current suite of bamboo standards. So ISO 22157 talks about the determination of physical and mechanical properties of bamboo culms, a test method standard. It deals with the physical characteristics of the bamboo that we're testing, density, mass per unit length, which is a very good surrogate for density when we're working with bamboo, and 6 mechanical test methods, from very simple compression and tension, bending, shear, and then tension and bending perpendicular to the fibers. And so all of these test methods are available as a suite that then will be able to support either grading procedures and eventually structural design with bamboo. And of course, we need to understand the material before we can possibly design with it. The 19624 standard is entitled Grading of Bamboo Culms, and that's a little bit misleading. It doesn't tell us how to grade bamboo culms per se, but rather, how to develop a grading protocol, a grading process, given a particular bamboo resource. And so it's very dynamic in that sense. Importantly, and I think supporting that effort, is the Annex A in this particular document, which is an example of how to develop a rational grading standard for a given resource. And grading is going to be very important as we move into the design standards as well, because we need to understand the resource that we're using in order to design with it. So finally, we have the 22156 document, which is structural design. And at present, this is a very modest document. It's limited to 1- and 2-story residential, light commercial, light industrial type buildings, and with a height limit of 7 meters. So we have a relatively modest scope. This was where the committee was comfortable, and our intent would certainly be that this scope will be extended as the document is revised in the future. The structural design document permits 2 methods of design. It permits what we call allowable capacity design, where we actually determine the strength of the individual members. So what is the capacity of a culm in bending? And this then requires grading. So we're not certainly going to be testing each and every culm that we place into a structure. So we need to understand the grade of that culm, and that grade will have a strength associated with it. And we also have permitted allowable stress design approaches, which are based on fundamental mechanics. At this point, we don't necessarily need a grading protocol, although it may help. What we need to understand are the fundamental properties of that material, couple those with geometry, and we have a method using fundamental mechanics to design with bamboo. Certainly allowable capacity design is probably preferable, and certainly leads to more streamlined design, and particularly the potential for producing load span tables, capacity tables, and whatnot based on grades. And we have illustrated the ability to do that. These are examples of design load tables for compression and for flexure of bamboo culms, examples of this. And so these are tools that are written in a manner that engineers are used to using and that we're very familiar with from other areas. And so that is one of the advantages of allowable capacity design. Now, the structural design standard also recognizes alternate design approaches. It does recognize that a lot of design, Eurocode design, some North American design, uses partial safety factor approaches or load and resistance factor design approaches. And so we have an annex in the 22-156 document that addresses how that can be done. We need to recognize that bamboo is a vernacular material, and there's a lot of success out there. There's a lot of bamboo structures that work really well, but that were not designed in a truly engineering sense. And so we recognize established experience, previous knowledge, and we also recognize that we need to have robust design by testing approaches, that we have to be able to take prototype structures, test them in the lab, address these from a statistical perspective in order to come up what is the strength, what is the capacity of a particular structural assembly. And this is largely based on the method adopted for timber structures for connections, wherein we have test methods that address rigorous testing protocols. We need an approach to interpret these protocols, interpret the results, in a uniform manner. And then finally, a method for correctly establishing characteristic design values. And this is not necessarily as straightforward as it seems. There are some examples out there now that we've done particularly with bamboo connections that illustrate this process. The current version of 22-156 also addresses so-called barricade construction. So light wall construction, where we have a light bamboo frame faced with a cement mortar to provide shear resistance. And this is a common form of construction in certain parts of the world. And we have an additional annex in 22-156 that provides prescriptive guidance, non-mandatory prescriptive guidance for ways to meet the design requirements for this type of construction. It is my opinion that in the next revision of 22-156, this particular material will be taken out and will form its own standard. These are slightly different types of constructions and probably should be handled separately. So I now want to move on to engineered bamboo materials. And so an example, nice picture that I have here of a glue laminated bamboo element. We recognize that we still need to understand the materials that go into this. And so we're still relying on test methods that might come from the 22-157 document. We can probably take advantage of grading as well when we start looking at selecting materials that go into these engineered products, where a higher grade material may go into a glue laminated we have a higher grade material may go into a glue laminated product, and a lower grade material might become a scrimber, which is, let's say, the third image down. And there's a number of engineered bamboo products out there, and we presently have a specification out there, ISO 7567, that addresses glue laminated bamboo. We have test methods that address then the products, the engineered products, in terms of member testing, 22478, and small sample testing, so small clear sample testing, 2557. And I think one of the advantages of moving in the engineered bamboo direction is that we can start looking in the same way that we do with glue laminated timber, start looking at engineered layups, use a combination of grading and testing to actually develop products that have been optimized from the point of view of from an engineering perspective. So then taking this and moving it to structural design. Presently, ISO is beginning to work on a structural design standard for engineered bamboo, but I'm going to make the argument here, and we have made it a little bit more formally elsewhere, that we can generally design engineered bamboo in the same manner that we can design engineered timber, and so that we can generally use existing timber design standards such as Eurocode 5, the NDS, CSA 086 in Canada. And we're leveraging the similarity between engineered wood and engineered bamboo. And what this does is it provides a confidence, it provides a reference benchmark that, coupled with advocacy for bamboo, can lead to the broader acceptance of engineered bamboo by the architectural engineering and construction community. And this will accelerate uptake. The key is to acknowledge the differences where the use of engineered bamboo requires limitation. So bamboo is highly anisotropic, much more so than timber, and also the components that we're using are much smaller. The laminates are on the order of 5, 6, 7 millimeters thick, rather than, let's say, a standard 2x, which might be about 38, 40 millimeters thick. So we do have some limitations associated with this. The high degree of anisotropy, hard word to say, I apologize, means that we have some significant limitations on dowel type connections, driven connections. You cannot nail into engineered bamboo. It just doesn't work. And also notch factors and notching. And one of the biggest significant changes or differences between engineered timber and engineered bamboo is actually in terms of its fire performance. Because of the small laminate size, we end up with an effectively greater char rate than we would see in typical softwood engineered lumber. And that really is a function of simply the small laminate size. As the fire reaches the first glue line, that outer laminate is assumed to have to spall off, exposing the laminate beneath it and so forth. If you think about that with a very thin laminate, you end up with a more rapid degradation of the material, and that needs to be addressed, and it certainly can be addressed, and we have some proposals out there for addressing this issue. It's still some questions associated with that. Engineered bamboo scrimber, on the other hand, is actually a very, very dense material, and because of that has been shown to generally have a better fire resistance than comparable engineered timbers, certainly closer to typical hardwoods rather than softwoods. So we are moving along. So what I want to do is shift gears a little bit here and talk a little bit about the activities of the Rilem Material Characterization of Bamboo Technical Committee. We're focusing on excuse me, a number of different things, and I just kind of want to summarize these a little bit. We're engaged in improving and developing material test standards. And so a couple of the things that have already been produced, we have a glossary of bamboo terminology. Terms used for bamboo around the world are all over the place. We all have a different term for different things. And so trying to normalize that a little bit, or at least allowing us to have a lingua franca, has been useful. We have also produced a laboratory manual, sort of a commentary for ISO 22157. There was originally an ISO lab manual for the 2004 version. Because of the way ISO promulgates test methods and documents, it wasn't really felt to be practical to write a lab manual for the newer version. And both of these have now been essentially completed. We are working on a state-of-the-art state of practice report that will also include issues of bamboo durability and treatment. So usually the elephant in the room, bamboo needs to be treated. It is not perceived as being particularly durable, and so how do we address that? And also state of the art of looking at measuring and quantifying bamboo sustainability. If we're going to justify bamboo as a construction material, clearly its sustainability credentials are a big piece of this. Interestingly, we don't have great quantifications of those just yet. I think some people may disagree with me, but again, the quantification is a little bit erratic, and so we're working on that presently. And those two, number 3 and 4 on this particular slide, are still underway. The Rilem Committee is also tasked with developing new test methods, improving existing test methods, and these will hopefully eventually be promulgated through ISO. So at this time, we've addressed 4 test methods. Largely, these have been reviewed and approved by the committee, and including language that looks like a test method, that they've been written in that sort of ISO language. These are flat ring flexure, small sample flexure, which really just takes advantage and allows us to use existing small sample flexure tests that are intended for fiber reinforced materials, fiber reinforced composites, and what are the revisions, what are the changes that we need to make in order to adopt those for bamboo use. A transverse bending test that sort of improves upon an existing test within 22157, and similarly variations on the 22157 shear test, which presently is a 4-plane test and permitting a 2 and indeed a 1-plane shear test. And those first 4 are essentially complete and ready for publication. There are other test methods that we are looking at developing: dowel bearing for connections, capacity of threaded connections into bamboo. There's interest in full-culm torsion and interest in terms of wettability and shear capacity of glued bamboo laminates, and so relevant specifically for the engineered bamboo community. And these will be assembled in a state-of-the-art report promulgated by the Rilem Technical Committee and hopefully by the end of this calendar year. Another important role of the Rilem Committee is to facilitate round-robin testing, establish precision and bias statements for these tests. And this is important because at the moment, the community views that we've got these 6 or 8 tests that are out there, and we have to conduct all of them in order to understand the behavior of bamboo. And that is probably not the case. Can we refine these to 1 or 2 critical tests that give us enough representative data, or data that we can use as surrogate for some of the other properties that we need? And the analogy that I use is simply for concrete. We infer a great deal about concrete, its tensile capacity, its modulus of rupture, its modulus elasticity from compression tests. And is there a way that we can do this with bamboo? We're not there yet, but that's probably the one test, the holy grail of the Rilem Technical Committee is, can we come down to 1 or 2 tests that are appropriately representative? So what is truly the grand challenge in addressing bamboo as a construction material? So there's probably about 100 species of bamboo on the face of the planet that are likely to be appropriate for construction use. They all have rapid growth, in which case they require they require constant characterization. Bamboo is affected by its growth cycle, is affected by the environment. And at the moment, we've adopted similar criteria, characteristic strength values as we write in timber. And the result of that is that under normal service conditions, it would be rare that the stress in bamboo will exceed about 20% of what's actually available. And so we're not necessarily using the material as efficiently as we might. And this, of course, affects economic and environmental costs of building with bamboo, and might deter designers from selecting bamboo as a material that they view as inherently unreliable, making advocacy a little bit more difficult. And so this is the challenge. And so how do we overcome this challenge? We can't possibly go out and produce the amount of data that we require. Think about steel construction or concrete construction. We have 150 years of data on which to build. We don't have that yet for bamboo. I'm going to look at a few ways of potentially addressing this challenge. First is material informatics, or the use of material informatics in bamboo. And material informatics essentially is a method of enabling discovery and optimization by defining process, structure, property relationships, the relationship between the process, the structure, and the property of interest. Now, when we talk about bamboo, we're generally interested in the structure-property relationships, the process being a natural process. The bamboo is grown, and we have less control over that particular stage. And in its simplest form, we can leverage simple rule of mixtures approaches with digital imaging techniques. This is what we're showing over here on the right, in order to enable discovery. And so what we're showing on the right-hand side of this slide very simply are the results of about 3,000 digital images of bamboo strips. These were reportedly essentially the same source, and were being used in engineered bamboo in the same manner. The engineered bamboo had the same, or allegedly the same material properties, and yet it was very clear when we looked at the feedstock, the bamboo strips, we had two very distinctly different batches involved in this particular data, and that's seen in the statistical data above. And material informatics allows us to see that very, very quickly. A second example, which I found absolutely fascinating, was we were looking at 3 different species of bamboo. In this case, a thicker-walled Tregai material and thinner-walled Moso and Guadua materials. And we were looking simply at the geometry of these materials. And so what we have plotted here are the diameters of the materials and or normalized diameter of the material, excuse me, and the normalized wall thickness of the material. And as we can see, we've got massive amounts of scatter. That's not particularly surprising when we're dealing with bamboo. But using sort of an informatics approach, we were able to classify these materials in a sense. We actually looked at the radius of gyration of the culm. Radius of gyration is the square root of the moment of inertia divided by the area, and the wall to thickness ratio. And what we found when we took this same data, we found a very clear species separation. The red data in the far right image is for a thicker walled bamboo species. It all falls radius of gyration to the right of 1, normalized radius of gyration, excuse me, all to the right of 1, and all the thin walled species are dominantly falling to the left. And this might indicate a way that we can start characterizing bamboo by species, maybe in a manner similar to the way in which we characterize softwoods and hardwoods. We could talk about thick-walled and thin-walled bamboo. Another approach to addressing the challenge of materials variability arguably is actually the use of marginally engineered bamboo, this sort of middle of the spectrum. Engineered bamboo has the advantages of relatively simple fabrication, relatively low cost. It uses a very high utilization of harvest. About 80% of the bamboo that's harvested can be used in a marginally engineered product, and this is greater than either full-culm bamboo or engineered bamboo. And to my opinion, marginally engineered bamboo probably has the greatest potential impact on the global construction sector. So finally, there are some other potential ways of addressing the challenge of variability. There's the concept of performative design, and in timber, performative design can achieve near 100% utilization of raw timber resources. And essentially, what we do in this case is we characterize each and every rough cut piece and use optimization software, use design software in order to create a structure that uses all of these pieces in the form in which they're found. So it's an interesting form finding exercise, and these approaches have been proposed for bamboo. They've not been demonstrated to my knowledge outside of the lab, but certainly hold also a lot of potential for increasing the utilization of bamboo using more marginal resources potentially. So with that, I want to conclude this talk and kind of sum up some of what I've brought to the table here. Today, bamboo is still reasonably considered a non-conventional construction material. The opportunities for bamboo as an alternative material that contributes substantially to reducing the global carbon footprint in the construction sector, it needs to be realized. We are slowly providing context-appropriate building standards and context-appropriate material standards to support these building standards, and these are being promulgated by ISO, and the Rilem committee is working on these. One of the problems and the challenges, with the exception of a handful of geographically specific bamboo resources, there really is very little information, reliable information on bamboo and material properties of bamboo. So suggesting applying a bamboo informatics approach can help to consolidate this gap by integrating materials research with the needs of the design and standardization of bamboo. The manner in which bamboo informatics is undertaken and ultimately integrated into design has to be useful. It has to provide good results, but it has to be globally accessible. It has to overcome socioeconomic and technical inequity around the world. Generally, we're not going to see a lot of bamboo construction in North America, in Western Europe. It's going to be in what we refer to typically as the global south. Nonetheless, the use of bamboo will always be limited by its inherent variability. Aggregating culm properties in marginally engineered bamboo assemblages, engineered bamboo composites, to some extent serves to mitigate the effects of individual culm variation in the same way that we do with engineered timber products. Additional engineering, however, comes with additional complexity and cost. And so I would make the argument that the less precise nature of marginally engineered bamboo, it's not as sensitive to the limitations imposed by fabrication methods. At the moment is less familiar to the construction industry, but to my view represents the greatest potential impact when considering the housing needs, and particularly the housing needs in the global south. Finally, what I've tried to do with this presentation is to provide a technical perspective for normalizing bamboo as a construction material, moving bamboo from the realm of non-conventional to just another tool in our toolbox. I have intentionally not addressed the social and cultural contexts of this shift. Bamboo is often, as we've probably all heard, it's referred to as being for poor people. It is rarely preferred over conventional materials which are thought to project wealth and progress. This paradigm, this aspect of this shift from non-conventional to non-negotiable is the subject of multiple different fields of study, of which I am absolutely not an expert, but this work has to go on as well. Nonetheless, technical acceptance, as illustrated by the development of the standards I've introduced here, and the priority application of cutting-edge informatics methods, coupling this with advocacy, can enhance the confidence and the cultural acceptance of bamboo, ultimately shifting, hopefully, bamboo as a construction material from being non-conventional to being non-negotiable. And with that, I wish to conclude. A great deal of this material that I presented here is also included in a recent paper, and I've got a link for that paper there, and the QR code is the link if for those interested. So now I believe we will shift back to being live and be very interested in taking questions.